So compound A, I will just take the drawer. So this is compound A with elements M and X. So M is given as a transition element that belongs to 3D block. So it can be scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and X ligands of the same type. So it can be like 3 water, or either 3 chlorines, 3 iodines, water, cyanide. So any other ligand that can combine with this element M and from this MXN complex. Okay. And then we have some information that was treated with this compound. So this compound was treated with excess dilute NaOH, followed by addition of H2O2, and this gives a compound B. So simply MXN, which is our compound A, and when you treat this with NaOH, excess NaOH, so you treat this with excess NaOH. Okay, so you treat this with excess OH minus, and then you add H2O2. So you should able to imagine what is happening when you add H2O2. So something is happening to this elemental compound. It can be either oxidation or reduction. Okay, so this forms compound B. And when an aqueous solution of B is acidified, so if you add a little bit of H plus, which is diluted H2SO4, and this forms the compound C, right? So if you have gone through your D block chemistry really well, from this point and the reaction with H2O2, you should be able to get an idea about what is M here. What is the transition element here? Because when B is formed after H2O2 addition, when you acidify, it is converted into C, which could be some compound that is related to a certain transition element that is in equilibrium with the acidic and basic solution, right? So what can be the element? I'm not going to tell the element, so you can think about that. And when we go furthermore, when C is treated with ammonium chloride, so we treat C with ammonium chloride, okay, it gives the compound D, which when you heat D, let's say heating solid D gives a blue color compound, so E, which is blue color, and they say it will give water and an inert diatomic gas. So at this point, you should be able to find what is this inert diatomic gas, why it is giving water, and what is E here, in fact, what is D here. Because if you remember, ammonium dichromate, okay, ammonium dichromate, we have learned when you heat it, it will give the inert diatomic gas, which is nitrogen. Then it will give water, as mentioned in the description, and it will give the blue color compound. So it can be Cr2O3. So you understand here, this is dichromate. So C should be Cr2 or some, okay, Na2Cr2 or some. So you know, I have explained to you in previous cases and also in my D block tutorial, this dichromate and chromate is always in equilibrium. So this should be Na2 CrO4. That is why when you add H plus, it goes from the chromate form to dichromate form. Okay, so what is the form when H2O2 is added to get CrO4 minus? So it should be surely chromium 3 plus. Okay, so that is the idea. So you can catch from this point heating solid D. This is the main point that you can catch what compound exactly is this. Okay, and we will go furthermore towards the description, and they say calcium metal when burnt with a gas F, so F is now nitrogen, and you add calcium, so you will form Ca3 and N2. Okay, and this is this solid precipitate that is called the G. And reaction G with water, so you know there is N3 minus. So when you react this with water, so it will form N3 minus. Since it has N3 minus, it will form ammonia and calcium hydroxide. Okay, so it gives you the idea. So when reaction with G, water liberate gas H. So gas H is ammonia. This gas form white fumes with HCl. So HCl with ammonia, it will form ammonium chloride, which is our white fume. Okay. The metal Na reacts with liquid H. So sodium react with liquid H, which means ammonia liquid, right? Which is going to give NaNH2 as one of the compounds plus hydrogen gas. Okay, so to give a colorless diatomic gas I, so it is H2 gas here that is going to form hydrogen gas as one of the products. So the other product is NaNH2. And when an aqueous solution of A, so this is A, is treated with excess sodium carbonate, a colored precipitate is formed. So you can imagine, so what could be this aqueous solution of A? So this is chromium 3 plus, because when you add H2O2, it will convert to CrO2 minus. So this could be like chromium chloride, or either chromium H2O6, 3 plus. Okay, so I prefer chromium H2O6 3 plus because we don't know whether this is a chloride or a bromide. Then when it is treated with sodium carbonate, so you can imagine what is happening when you treat this with sodium carbonate. Chromium carbonate is going to form, or either when you treat this with sodium carbonate, which is a little bit of a basic in nature, and when you have done the precipitation, you can imagine what is going to form. Okay, and everything is here in the description. So, and finally the precipitate is filtered, and filtrate is acidified with diluted HNO3, and adding AgNO3 to the solution gives a white precipitate which is soluble in dilute. So this is going to form so here the chromium carbonate is going to form, and then the precipitate is filtered out. So you have the acidified solution with dilute HNO3, and when you add AgNO3, the solution gives the white precipitate. Okay, so again, chromium, it is soluble in ammonium hydroxide. So the first point is identify all these A, B, C, D, E, F, G, H, and I. So we have identified all these A, B, C, D, E, F, G, H, I, everything is identified, right? So up to A to I is identified. And then what will you observe when a solution C is treated with dil NaOH? Give the balanced chemical equation. So nothing happens. So basically, it's the equilibrium that gives the shifting because oxidation state is same. So C is sodium dichromate. So you have Cr2O7 2 minus, and when you add OH minus, so you add OH minus here, so it will be transferred to CrO4. Sorry for the writing. This is 7. This is chromium, so this is 2 minus, and CrO4 2 minus. So you have to understand here the oxidation state is not changed, so this is H2O. You can balance by putting 2 here. Okay, oxygen, I guess oxygen is balanced, chromium is balanced here. 7, 9, so 8 and 9. So this is the reaction that is going to happen here when you add NaOH. But don't forget, this equilibrium we normally study in this way. I can show you our reaction scheme. So if you can remember, it's here. So this is the normal equilibrium that we study in water, right? So CrO4 2 minus, Cr2O7 2 minus, CrO4 2 minus. So when you have H plus, when you add OH minus, what is actually happening? So H plus is removed, this equilibrium is shifting towards the right hand side, and more CrO4 2 minus is formed. So you can write down this equilibrium in this way, or either when you have dichromate and you add this OH minus, so CrO4 2 minus, and water is formed. Okay, so this is what actually happens. So everything is there if you go through this block tutorial, as I have mentioned you before. Even this one, when you have chromium 3 plus, you add H2O2 with the OH minus, so CrO4 2 minus is formed. And CrO4 2 minus, you can imagine when you acidified, it will convert to Cr2O7 2 minus, as explained in this previous equilibrium reaction. It's here. H plus medium, acidic medium, it gives dichromate. And when you add ammonium chloride, according to the description, they say, so it is formed, everything is there. Okay. So this particular question is not hard. You can easily answer this one because everything is given, right? So you can imagine what is actually happening when you do all these things. Then part B. So part B is a description. So we will go through it very quickly. So aqueous solution T contains 3 metal ions. The following experiments were carried out to identify these metal ions. So we will check. T was acidified with diluted Cl or K, and H2S was bubbled through the clear solution obtained. A black precipitate. So this is the formation of the sulfides in the acidic medium. So what can be the sulfide that can form in the acidic medium that gives a black color precipitates? So it could be HGS, CUS, and Bi2S3, and then PBS. So these precipitates can be formed, right? So Ag2 plus, Cu2 plus, Bi3 plus, and Pb2 plus. So these precipitate can be formed in the acidic medium. Then they have mentioned they have filtrated the solution and add ammonium chloride and ammonium hydroxide. So a clear solution was formed. So there is no hydroxide that is going to form in this solution. But when they send H2S again, so they were able to again see a black precipitate. So this is sulfide precipitation under basic condition. So under basic condition, so what can be the precipitate? So you can have black precipitates are cobalt sulfide and nickel sulfide. So these two are the black precipitate that you can observe under basic condition, which are black. So other than that, you know, we can have manganese sulfide, which is pale pink, and zinc sulfide, which is white in color. And again, Q2 was removed and filtered. You add ammonium carbonate. So this is the last group, group 5. So white precipitate is formed. So you know, strontium carbonate, so strontium 2 plus and barium 2 plus can be there, or calcium 2 plus. So these are all white color precipitates. Okay. So we have to identify which element is there, because only 3 is there. Up to now we have like 4, 2, 6, 3, so 9. So we have to remove 6. So we will come to the experimental procedures for the precipitates. Okay. So Q1 was dissolved in hot dilute HNO3. So we have these compounds. So we dissolve this, and after the cooling, we neutralize this and add with Ki. A precipitate and a brown color solution were formed. So this is important to identify this one, which it could be. So when you add Ki to this soluble forms, a precipitate and a brown solution is formed. So when you think about these elements, when you solubilize this and neutralize and then add Ki, so Hg2 plus will form Hgi, Bi2 will not add, PbIv is formed. But when you add copper, when there is copper 2 plus, I think you should be able to remember this at this point. So when you have I minus, if you can remember, we studied this one, it forms copper iodide plus I2, which is brown in color. This is our precipitation. Okay, so don't forget, this is copper is reduced, I minus is oxidized to I2, but since CuI is a precipitate, so we will observe this precipitate as well. So we confirm here it should be copper 2 plus. Okay, and then this is U, copper 2 plus. And for the second precipitate, which is our sulfides, so in the basic condition, so Q2 was dissolved in warm dilute HCl, so this is dissolved, and solution was good, and dilute ammonium hydroxide was added, so its hydroxide can be formed, and a green precipitate was obtained. So can you think about which is the green precipitate? So it could be cobalt hydroxide, yes, which is dirty green, we say. Nickel hydroxide is also a little bit of green, so we cannot confirm yet. More dilute NH4 was added to the mixture. The green precipitate dissolves, giving a deep blue solution. So now we could imagine what is actually happening, because dilute, when you add more dilution, so when you add more dilute NH4OH, out of this, when you have this HCl as well, and when you add more and more and more, which of these precipitate gets dissolved? So it is basically the precipitate is, which one is it? Cobalt or nickel? That is what you have to find from this thing. Cobalt, when you add more and more OH, it will form cobalt OH6, and cobalt even not familiar with forming complexes with excess amount of NH4OH. But what is this deep blue color? It should be surely nickel hexaamine 2 plus solution, right? That is why it gives a deep blue color solution. So the element here should be nickel. Here it should be copper. And finally, we are remaining with strontium, barium, and calcium. So Q3 was dissolved in concave Cl, and the solution was subject to flame test. So very easy flame test if it is green, so it should be Barium 2 plus. So barium gives an apple green color in the flame test. So it is easy to identify, right? So we have identified the metal ions. So identify the 3 metal ions in solution T. So reasons are not required. So even though the reasons are not required, but when you try to analyze, you should argue in this way and try to get the precipitate. So Q1, Q2, Q3 chemical formula of the precipitate. So Q1 is copper sulfide, Q2 is nickel sulfide, and Q3 is barium carbonate. Okay. So this is also a very nice, straightforward question. Right. So we can move to question number part C. So this question was talked a little bit more because even though this question is like a lengthy one, the it's very simple question actually. Okay. The following procedure was used to determine the concentration of aluminium 3 plus ions in solution U. So excess 8-hydroxyquinoline, which is commonly used known as oxine. So we use this in our university to characterize aluminium, in fact. So there is a solution U and its volume is given as 25. So this oxime is added. So this type of a reaction is going to happen. And this oxime gets precipitated. So it will form the aluminium oxinate. And this precipitate was filtered and washed with distilled water. And it was warmed and dissolved in HCl. And KBr was added to it. Thereafter, 25 cubic centimeter of so when you do this process up to here, right? So the solution contains the dissolution, that means this one and this one. Additionally, you will have Br minus because KBr is also added. So all these are present at this point, right? Then what they have done, so they have added 25 cubic centimeter of 0.025 KBrO3. So here they have added 0.025 m 25 cubic centimeters. So you can calculate the moles, right, of BrO3 minus added. And when you add these things, remember, Br2 is formed. And now this Br2 that is formed because of the reaction with BrO3 minus and excess KBr that was already present in the solution. So this is the solution that is already present, okay? This is the solution that is already present after the dissolution and everything, right? And this released Br2 from this particular reaction after the addition of BrO3 minus. This is react with this particular oxime that is formed from the dissolution, you see? And this is formed. And they say excess Br2 is reacted with Ki. So there is a reaction that is happening. Br2 with I minus is going to form 2Br minus and I2 because this is oxidation reduction reaction. So this is the reaction that is going to give I2. And this is given as I3 minus because since in the solution has excess I minus as well, so this I2 reacting with I minus always be present as an equilibrium as I3 minus. But no worries, you can get this as I2. Okay, so they say excess Br2 here after the reaction with oxime, some amount of Br2 is remain. Okay, so this is the remaining amount. So remaining amount is there remained, and this react with Ki to give I3 minus, which is our I2, and this was titrated with Na2S2O3. So you know the typical reaction up to now. So you know this will form NaI and plus Na2S4O6, right? So this is a very typical compound that at this point you should be able to know. And they have given the amount that is consumed. Sodium thiosulfate was 0.05 m, and the volume needed was 15 cubic centimeter. Right? So you can put here 2 and put here 2. The stoichiometry between sodium thiosulfate to I2 is 2:1. Then they are asking calculate the concentration of aluminium 3 plus in solution U. Right? So we will discuss this first in a qualitative picture. Right? So initially this mixture was formed. There is a circle through the red color one. Right? So you can calculate the amount of BrO3 minus here that you used actually. And based on that, you can calculate the amount of Br2 that is formed, right? And through this excess Br2 that is present, you can find this using this one, because you can find the amount of sodium thiosulfate that is used here. Based on that, you can find the amount of I2 that is present in this solution. And if you know the amount of I2 present in this solution, you can find the excess Br2 that is present in this solution. So you know the amount of total Br2 that is formed from here. This is the total one, right? And through this procedure, you know the excess one, right? This is known. So you can calculate the amount of Br2 that is reacted with the oxime. That is this total amount. Let's say this one as x1, and this is the excess amount. Let's say this is as x2. So the reacted amount will be x1 minus x2. Okay. So if you know this amount, which means you know the oxime amount, because it will be 2:1. So this amount will be x1 minus x2 divided by 2 according to the stoichiometry. So this oxime is present here. So this one will be x1 minus x2 divided by 2, which we found here. And if you know this amount according to the stoichiometry, this is 3:1. So our aluminium 3 plus in this solution will be again divided by 3. So this is the total amount of aluminium in this solution. And if you know this aluminium in this solution, you know the volume that we used, that was 25 cubic centimeter. You can find the concentration of aluminium. But don't forget, they have mentioned to find this in milligrams per decimeter. So finally, when you find this in MOLDM minus 3, you can multiply it by aluminium molecular weight to get in the gram, then multiply it by 10 to the power 3 to get this in milligrams per decimeter. Okay. So this is how you can do. These things are lengthy, right? But this calculation is very simple. Okay, because you can get the excess Br2 formed here using this information from the sodium thiosulfate titration, and you can get the amount of total Br2 formed from this BrO3 minus, which is added. You subtract this, you get the Br2 that is reacted with oxime. So you can divide this by 2 to get the amount of oxime. And if you know the amount of oxime, you can divide this by 3. So this oxime is calculated here, and you divide it by 3 to get the aluminium 3 plus moles. And you know the solution volume 25, you can find the concentration and express that as in milligrams per decimeter. Okay. So this is a simple explanation for this particular question, right? So this ends our question number 8. I hope you understood this. So you can calculate the moles here. It will be 0.02525 into 10 to the power minus 3 times 3, because Br2 stoichiometry is 1:3. So you know x1 here. And here you calculate the total sodium thiosulfate moles, 0.05, 15 into 10 to the power minus 3. Then I2 is half of that. and it will be same to Br2. So you know X2 then. So X1 minus X2, you know the amount of Br2 reacted. So you divide it by 2 to get the oxime. And this is all oxime that you have. So you divide this again by 3 to get the aluminium 3 plus. And you divide it by 25 into 10 to the power 3 to get the MOLDA minus 3. And you multiply it by 27 into 10 to the power 3 to get in milligram. That's it. Very simple calculation.